In this lecture, we will talk in detail about NLP. Since the beginning of humanity being able to transfer your ideas of what you think about to another human being is one of the major factors that boosted our evolution as a species. Otherwise, how would you tell your fellow human, let's be friends and build a community where we'll protect each other from Mother Nature's dangers or from others? Communication and the ability to understand each other was the key. Now let's fast forward to the times that we invented machines. Of course, we made them to make our life easier to some extent. Machines helped us transforming industries and also in wars. With the invention of computers in 20th century, we witnessed a major progress in how we use machines, where computer devices played a big role. In order for humans to utilize these so-called computing devices and communicate with them, we created what we call programming languages. A programming language is considered as the only means of communication between a human being and a machine, or computer to be more specific. We could show computers what we want them to do or which tasks they should perform at which time. But in order to communicate with computers or to talk with them, which means build an app or a piece of software to control them, one needed to either speak binary like computers or be a wizard who mastered the art of writing code. At this point, you might be wondering how all this is related to natural language processing. Well, check this out. The solution to give everybody the possibility to talk to a computer, sparing them the time, effort, plus the coffee cost to learn how to program, was to teach computers how to speak human languages in order for them to understand us. That means we needed to teach them natural language. If you Google what is natural language, you will find out that it's any language that evolved naturally through use in repetition, without conscious planning or premeditation, as stated on Wikipedia. Adding that to the fact that NLP stands for Natural Language Processing, we can draw the following conclusion. NLP is a field that focuses on computers' ability to understand and process human languages. A database uses structured data, a data that follows a certain specific form, so it's easier for computers to understand which piece of data means what exactly. But with the spoken languages, the structure is totally undefined and unprotected, and that's what makes it really hard for computers to understand us and also communicate freely and fluently with us. But with the rise of artificial intelligence, especially machine learning, into recent years, we have the possibility to write programs that can help translate, understand semantics, and sentences to some extent. But we are not doing it perfectly yet. The road is still long before a computer can talk to a human the way the human can talk to a human. That's why your smartphone is able to understand what time is it, but it cannot process complex statements like I think, therefore I am. To talk with humans, a computer must be able to understand the syntax or grammar and morphology in any given sentence in a given language. Now let's go over some common NLP tasks. First, let's start with tokenization, which means spreading the text into tokens, minimal meaningful units. And this unit can sometimes be words or sentences. So, we tokenize an article into sentences or into words, and of course, also a sentence into words. Now let's see part of speech. This means assign a part of speech to words in the text like noun, a verb, adjective. Then we have stemming. Stemming is the process of reducing words to its stem, like walking can be reduced to walk. Same way, lemmatization, it's a similar concept to stemming except that it operates also by including the knowledge about the word's context, like good and better. Then we have named entity recognition or NER, which labels the sequence of words that represent the names of things like a person, company, or a street. Now, we have something what is called as parsing. A parser will let you analyze the grammar of the text so that you can extract or determine the same text form. Soon, we will be talking about some of the tools and libraries which we can use to perform these tasks. But first, let's jump into what actually natural language processing means. There are various definitions out there, but natural language processing is a field that's concerned with the ability of a computer to understand, analyze, manipulate, and potentially generate human language. By human language, we are simply referring to any language used for everyday communication. This can be English, Spanish, French, anything like that. Now, it's worth noting that Python doesn't naturally know what any given word means. All it sees is a string of characters. For instance, it has no idea what the word natural actually means. It sees that it's 7 characters long, but the individual characters don't mean anything to Python. And certainly, the collection of those characters together doesn't mean anything either. So, we know that what an N is, what an A is, and we know that together that those several characters make up the whole word natural, and so we know what that means. So, NLP is the field of getting the computer to understand what naturally actually signifies, and from there we can get into the manipulation or potentially even generation of human language. You probably experience natural language processing on a daily basis, and you may not even really know it. So here are a few examples that you may be able to see on a day-to-day basis. The first would be a spam filter. So this is just where your email server is determining whether an incoming email is spam or not, based on the content of the body, the subject, and maybe the email domain. The second is the autocomplete feature, where Google is basically predicting what you are interested in searching for based on what you have already entered and what others commonly search for with those same phrases. So if I search for natural language processing, it knows that there are many other people also interested in learning NLP with Python, or learning it through a course, or looking for jobs related to natural language processing. So it can autocomplete your search for you. The last is autocorrect, where say an iPhone is trying to help you correct a misspelling. I like this example because it shows how autocorrect has actually evolved over time and continues to evolve and learn. So with an iOS 6, if you are trying to say I'll be ill tomorrow, it won't necessarily correct I'll be ill tomorrow until iOS 7, where it actually corrects, it autocompletes tomorrow and corrects I'll to ill. So it will correct send as I'll be ill tomorrow. So that just kind of shows how NLP is still evolving, and even super powerful systems like iOS is still kind of learning what natural language even means. Now NLP is a very broad umbrella that encompasses many topics. A few of those might be like sentiment analysis, topic modeling, text classification, and sentence segmentation or part of speech tagging. The core component of natural language processing is extracting all the information from a block of text that is relevant to a computer understanding the language. This is task specific as well. Different information is relevant for a sentiment analysis task than is relevant for a topic modeling task. So that's a very quick introduction into what natural language processing is. Now let's start thinking about the tools that we actually need to build these processes. The Natural Language Toolkit is the most utilized package for handling natural language processing tasks in Python, usually called NLTK for short, and it is a suite of open source tools that were originally created in 2001 at the University of Pennsylvania for the purpose of making building NLP processes in Python easier. This package has been expanded through the extensive contributions of open source users in the years since its development. NLTK is a great resource, and basically it provides a jumpstart to building any NLP processes by giving you the basic tools that you can chain together to accomplish your goal rather than having to build all those tools from scratch. A lot of tools are packaged into NLTK, and in the next section we'll be diving down into the downloading of the package and exploring some of those tools. Let's jump into actually getting the natural language toolkit set up on your computer. Now in cell 1, you just type !pip install nltk and run it, and this will install nltk. Then in next cell 2, you can start by simply importing and downloading the data to explore this package a little bit. Now we have to add this download step here because NLTK includes all kinds of corpuses and functions, and it actually downloads some of this to your local computer. Now when you run this, it's going to open a new window asking you what you'd like to download. So if you have already downloaded it before, you will exactly see what I see here, where it just indicates that all parts of the package are already installed. Now, if you don't have it already installed, what this allows you to do is pick the parts of the package that you would like to have installed. So you will just highlight what you would like, and in that case, you should install all of them. So you would highlight all of them, click the download button, and you are going to give it a few minutes. It typically takes 3 or 4 minutes to install everything. Once it's done installing everything, then you have to go ahead and close this window, and that will let NLTK know that you are done installing what you need and you are ready to use the actual package. So in cell 3, let's look at what's actually contained in the package. So I'll do dir parenthesis NLTK, and that will print out all the functions and attributes and methods within this package. So this list is incredibly long. We won't have the time to explore 99% of these. So I strongly encourage you to dive into some of these just to learn what NLTK is capable of. It's a really powerful package. Now I'll call out just a couple of things outside of what we are actually using in this lecture. So if you find this pos_tag, now if you recall back from the slides previously, I mentioned that part of speech tagging or POS tag as one of the components of natural language processing. So this is the actual function within the natural language toolkit that will actually do that for you. So we are not going to use that in this lecture, but it's a useful function to know, and I would strongly encourage you to explore using that. The other function that I want to call out is the tokenize function. Now this will just take a sentence and split it into a list of words that make it easier for Python to digest what it's supposed to be looking at. Later, we are going to actually tokenize ourselves, but we are going to build our own function to do it. And the only reason that I did that is so that you can better understand what's actually happening under the hood and how this actually works. Moving forward, you can feel free to actually just use the function to do it. It's much faster than building your own function to do it. Now in cell 4, let's dive in and actually experiment with one small component of NLTK. So we are going to take a quick look at some stop words just as an example to see how you call certain things from NLTK. So it's not important to remember that specifically. So we'll start by telling it that we want to import stop words from nltk.corpus. So from nltk.corpus import stop words, and then to actually look at the list of stop words, we'll type in stop words and then we'll tell it we want the actual words there. And there are stop words in different languages, so we'll tell it that we want the English stop words. And it's a fairly long list, so we don't want to look at the whole thing. So we'll just print out the first 10. So we'll see I, me, my, myself. So it's a lot of pronouns here. Then in cell 5, let's take a look further down the list, and what we are going to tell Python is to start at the 0th element or the element in the 0th position and go up to the element in the 500th position, and we only want to print out in increments of 25. So when we run that, you will see that there's also been, with, here, very, and things like that. Again, we will get into this in more detail later on, so it's not necessary to remember this now. But stop words are basically words that are used very frequently but don't really contribute much meaning to the sentence. For instance, you may be trying to do sentiment analysis, and these words are generally sentiment neutral, so there's no strong meaning necessarily one way or the other. They are just clouding the signal and taking the room away from words that aren't sentiment neutral. So we can go ahead and safely drop these. Again, we'll be digging more into this later on, and it's not important that you know exactly what stop words are, just that it's useful to see how you can access a specific corpus of words in NLTK. So, this was a very quick introduction and a very high level overview of some of the attributes and methods contained within the NLTK package. We'll get into more details as we move forward with this section. Now that we have learned the basics of what NLP and NLTK are, we are going to continue the process of assembling some tools and knowledge that we'll put to use as we move forward in this course. In this lecture, we are going to learn how to read in semi-structured data. This probably isn't something you really think about if you are used to reading in well-formatted CSV or PRK files in the past, which would be represented by this nice column or row-based depiction on the left. But reading in text files can be a little bit of battle sometimes, represented by this figure on the right. Text data will typically be in semi-structured or unstructured format. So, I've mentioned unstructured a couple of times. What does this really mean? Well, it could mean that it's binary data, it could mean no delimiters, or it could mean no indications of any rows. A few examples might be an email, a PDF file, a social media post. These may just be dumped together in a file with no indication of where maybe a subject of an email ends and the body of the email begins, or even where one email ends and the next one begins. It could be cluttered by things like HTML tags, and we won't really get to know it, and we won't really get into it in this lecture. But the idea is just that it can get really messy. So it's important to note that Python is pretty smart, but ultimately, unless it's told otherwise, it basically sees everything as a string of characters. It needs to be told what those characters mean. So, to illustrate how to read in semi-structured data, we are going to be using a dataset from the UCI machine learning repository. This dataset is a collection of text messages, each with a label of either spam or ham. We'll be using the same dataset for the duration of this lecture, and I'll be providing you the link to it. Now, before we dive into this, I want to show you what the raw text file looks like, so we know that what we are working with. It's not a clean CSV file, but it's not terribly unstructured either. Each row has a distinct text message and a distinct label as either spam or ham. So, in the context of text datasets, this is actually pretty well structured, and so this shouldn't be too difficult. Now let's jump back to our notebook. So in cell 1, we are going to start by opening this file and just reading it, which basically just means that you are pulling in the text without any resemblance of the structure at all. You may do this even if you don't know what your data looks like and you're just reading it in. This gives you a way to get a first look at the data, and then you can continue to determine your next step. So we are opening it and then we are reading it. Note that this section is as much about text manipulation as it is about reading in a file. The way we'll read this in certainly isn't the easiest, but many times you don't know what the easiest way is upfront, and you'll have to explore the data first. Additionally, I don't want to limit you from taking on a more complicated dataset moving forward. So we are going to take a roundabout and inefficient way to reading this with the purpose of arming you with some tools that you'll need to take to explore more difficult datasets later on. So we've read in our dataset with this open.read. Now let's print it out and take a look at what's contained in here. So because we've read it in without any indication of format, it doesn't know if there are any rows, columns, words or anything. All Python sees is a very long string. So coming to cell 2, to tell it how much to print out, we basically just tell it how many characters. So we are telling it print out the first 500 characters. So now you could see that it's just basically a block of text, and you will see that you have these /t and these /n separators. The /t's are between the labels and the text message bodies, and the /n's are typically at the end of those lines. There are many ways to tackle this. The way that I am going to do it is replace the /n's with /t's, and that will allow us to split this into a list, and then we can move forward from there. So in cell 3, what we are going to do is we are going to assign this to a list called passed data, and then we are going to pass in, say we want to use this raw data string, and what we are going to do is we are going to use this replace function. What that's expecting to see as the first parameter is the thing that it's looking for. In this case, it will be /t. Then the second parameter is what it's going to replace that with. In our case, we are going to do /n. So every time it sees /t, it will replace it with /n. And what this allows us to do is then do a dot split. And what this will do is take our string and split it on a certain character and return a list. So we'll tell it split on /n, and now every time it sees an n, it will chop off and add that component to our list. So in cell 4, if we run this, then we'll print out the passed data. Instead of printing out the first 500, now it's an actual list. So we'll just print out the first 5. Now you can see that this is basically alternating where your labels exist and your 0th position, the 2nd position, the 4th position. So it's every other, and the same thing with the actual labels. So this gives us some sort of structure. So in cell 5, what we are going to do is we are going to create a new list called label list, and what we are going to do is we are going to pull from that passed data list every other item. So what we tell it is passed data, and then we want to start in position 0, so that will be the very first one, and then we'll tell it we want to go to the end, so we don't enter anything in the second place, and then we tell it 2. So what that's telling it is start in the 0th position, go to the very end, and take every other. So it will grab ham, spam, ham, and so on. Now we want to do the same thing for the text lists, so we can get the text bodies in a different list. So again we are taking passed data, but this time it's going to be starting in the position 1, which is the second element in the list. So we'll start this with 1, and it will grab every other one. So when we run that, and then let's take a look at the first 5 entries of label list, and then we'll take a look at the first 5 entries of text list, just to make sure that it did what we expected it to do. And in cell 6, we'll go ahead and print both of these, because if you don't include the print statement, Jupyter Notebook will only print the most recent statement. So it would print text list and it won't print label list. So we'll add the print statement on both, print those out, and we can see that the lists are separated in the way that we expected them to be. So now we have the information that we need to separate into 2 lists. So we can now start thinking about combining these in a way that we can use for actual analysis. So in cell 7, the first thing we want to do is import pandas. So just do import pandas, and then we are going to save that as PD, so that we don't have to call pandas every time that we need to use one of its functions. So we are going to create a data frame that we'll call full corpus, and the way that we create this data frame is call pd dot call the data frame method, and within the data frame parenthesis, and we are going to need to pass it a dictionary, where in the dictionary the keys are going to be the name of the columns, and then the values will be the lists that we've stored the actual values in. For the first column, we'll call it label, and we'll pass in label list, because that's where the actual values are contained. And then in the second column, we'll call the body list, and we'll pass in text list. So what this should create is, it will take label list and text list, create a data frame out of them, and then label the column names, label and body list. So let's go ahead and print this out. We do a full corpus dot head, and that will print out the first 5 rows. And so we get an error here. It throws an error saying that arrays must have same length. So let's dig into that error. So we are going to check the length of each of these lists to see where the issue lies. In cell 8, we'll do print len label list to print the length of that list, and then we'll do the same thing for the text list. Print those, and you see that label list has one extra entry that text list does not have. My guess is it picked up on something at the very end that is creating the mismatched length. So in cell 9, let's print out the last 5 items of label list. So the way we print out the last 5 items is we do a -5 till the end. So what that's saying is go to the very end and count 5 backwards and print out those last 5. And you will see here that the very last entry here is empty. So it's picking on the extra entry that we don't need it to. So in cell 10, if we just drop that, then it will have the same length as text list, and they'll match up because we are going to be using the same exact thing to create our data frame. The only change is that we are going to tell label list, instead of grabbing all of them, just don't grab the last one. So this says start at the beginning and capture all of them except for the very last one. So now when we do full corpus and print out the first 5 rows, it should print out the way that we expect it to. And so now you have a nice clean version compared to what we had over here, where it was rather messy and you could see some structure, but now it's all cleaned up where it's all in the data frame, and now you can start to do some actual analysis with this. Now I'd like to revisit the fact that I mentioned earlier we would take a bit of a roundabout way for the purpose of arming you with tools to tackle more difficult datasets. In cell 11, to give you an idea of where we could have taken a shortcut to reading this in, as soon as we noticed the /t up here, that tells us immediately that this is tab delimited. Pandas allows you to read in tab separated files very easily. You learn that different details like /t are giveaways to allow you to take these shortcuts, essentially to reading in your data. The easiest way to actually read this in will be to use the read CSV function from pandas. So we'll assign this to dataset, and then we'll call pandas.readcsv, and we'll just pass in our spam collection dataset. And the thing that tells it that it's spam separated is there's a separator parameter here, and we'll tell it /t. So that tells it that it is tab separated. And the only other thing that we need to add in here is header is equal to none. The reason we need to do this is because the raw dataset does not have column names, and if we don't say header is equal to none, it will take the first row and assume those are the column names. So let's just go ahead and print this out. And as you can see, the column order is switched, but it's the same content, and there's no column labels here. So in this section, we took a dataset where we didn't have any idea what the structure was, and we explored it to uncover the structure of the dataset and organize it in a clean way. So now it's prepared for the next steps in our NLP pipeline. Previously, we learned how to read in our dataset the difficult way to arm ourselves with some text manipulation tools, and then we learned the easy way using pandas read CSV function. Now we are going to read the data back in the easy way. So again, in cell 1, we are importing pandas and storing it as PD, and then we are calling pd.readcsv, where all we have to do is pass in the name of the dataset. So that's SMS spam collection.tsv, and then we have to explicitly tell it what the separator is. Notice that the tsv extension means tab separated file, and thus we need to explicitly specify the separator as tab/t. So we'll tell it \t, which indicates tab separated. And then lastly, that it shouldn't expect a header. In other words, if we don't include the header is equal to none, it will take the first row as the column names. Then we are storing this as the full corpus. Now, as we saw previously, there won't be any column names in the data. So let's go ahead and actually tell it what our column names are. So let's call it full corpus dot columns, which just stores the column names, and then we can simply pass in a list. So we want the label to be called as label, and then we want the text message to be called body underscore text. Now let's go ahead and just print out the first 5 rows of this data frame. There it looks like just what we did last time. Now typically, before diving into any in-depth analysis, data cleaning or model building, we want to do some very high level exploration of our data to understand what we are working with. So we might ask some questions like, what is the shape of our data? How many ham or spam are there in our dataset? And are there any missing values? So this will inform the decisions that we make as we move forward. So in cell 2, let's start by shape. So this will help us understand how much data we have to build a model on and how many columns there are. To make this clean, we'll use print statements so that we can say input data has this many rows and this many columns. And then in order to fill that, we just have to do dot format. And then we'll pass in the number of rows which is filled simply by len full corpus. That will fill the first bracket, and then for the second bracket, we just have to do len full corpus dot columns, just like we assigned above. So then when we run that, it will just tell us how many rows we have and how many columns we have. So for this dataset, it's pretty obvious that we can just count the number of columns. But it's more important as you have a couple of million rows and hundreds or thousands of columns. In that scenario, you won't be able to count the number of columns. So this can actually be pretty helpful. Next, in cell 3, we want to know how many rows are spam and how many are ham. This is especially important as we move towards machine learning. If something like 5560 out of 5568 are spam, then we would approach this problem in a different way than if it were a 50-50 split. So we are going to use the same format for the print statement as we did previously. So here I'll say out of this many rows, this many are spam and this many are ham. And then again, in order to fill those brackets, we just do to get how many spam we have in our dataset. And we'll go to a new line, and then again, we are still going to take the length, but we'll take the full corpus, and then we need to filter the full dataset to only include the rows where the label is equal to spam. And then we close off our len parameter. So again, what this is doing is, it's taking the full corpus dataset and it's filtering it to say the rows must have label equal to spam. And so that will filter out the dataset down to only rows which have labels of spam. And then you take the length of it, and that will tell you how many of your text messages are labeled spam. So now we need to do the exact same thing for ham. So now this will filter your dataset down only to the rows or text messages that have a label of ham. And when you run this, it tells you out of 5568 rows, 746 are spam and 4822 are ham. So we can see that the data is fairly lopsided. This is important information as you start to build your machine learning classifier, and even later on when we start creating features, this will be useful to know. So we'll revisit this again in the feature engineering section. Now lastly, in cell 4, we want to understand how much data is missing here. If we have text that's missing, then we won't be able to use it to build a model if we are missing the actual body text. So we want to know that ahead of time. So again, we are going to use the similar format with the print statement, and this one will say number of nulls in the label and add that bracket, and then again we do format, and in order to get the number of nulls in label, we do full corpus label, and then we can use this isNull method. And what the isNull method will do is it will look at the entire column of labels, return a true or false for every single one. So if a label is present, if it's either spam or ham, then it's false because it is not null. and if it is missing or it is null, then it will return true. And then what we can do on the end of that is add dot sum, and that dot sum will just add up all the trues, so that will return how many nulls are there in the labels. So we want to know the same thing for the text body, so we can just copy this down for the body text. So it will look for nulls and assign a true if it is missing, and then we sum up all the trues. So we can run this, and luckily we don't have any missing values, which is going to be really helpful. So this section helped us better understand our data once we actually got it read in. The insights pulled from this very basic exploration will help us dictate how we approach the rest of our data cleaning and model building. Now that we know how to read in messy text, we want to learn some of the basics for how to manipulate, search, or split that text. So, in this section, we are going to cover some basics on regular expressions. If you are new to regular expressions, a regular expression, or a regex for short, is a text string used for describing a certain search pattern. So, if you are familiar with wildcards for search, like if you wanted to search for any CSV file on your computer using start.csv, this is basically just a supercharged version of that. Regular expressions can take various forms that we'll experiment in the next section. But to give you a quick example of what I mean, this regular expression will just search for the explicit NLP string within some other string. This isn't so much a search pattern as it is an explicit command for what we want to find. So if it was I love NLP, then the search pattern would just capture and return NLP. Another way to define the NLP string would be to use this expression, and this will just search for all characters between J and Q and in whatever text we are looking at. But this will search for all characters between J and Q and not just N, L and P. The other consideration here is that it will return only single characters at a time. So this would return N and then L and then P, and also whatever other characters between J and Q in your text string. This isn't usually what we are looking for. So we can solve this issue of only returning a single character by simply placing a plus sign outside of our brackets. What this will tell Python is that it can search for strings longer than one character. So what this will look for is any character between J and Q, just with the added flexibility of returning strings of multiple characters together that are between J and Q. Now switching gears a little bit, this one will return all numbers with the flexibility of returning sequences of more than one number. So if there is an year like 2017, it will return the full year rather than each number individually. Then lastly, to combine these two concepts, this will search for sequences of characters between J and Q or numbers between 0 and 9. So if you had a course name that was NLP 2017 without any spaces, then it would return that full string. But if you had NLP space 2017, that is, there is a space between NLP and 2017, then that would return them as two separate sequences. This is just 5 very quick examples, but there is literally an infinite number of patterns that you could come up with, and regexes give you the power and flexibility to search for almost any kind of pattern that you would imagine. The examples are useful, but why do we actually care about this? Now, regexes are particularly useful when dealing with text data because a lot of the data is unstructured, and where you need to be able to use these patterns to create some structure within the document. For instance, you could use a regex to identify the space between words or tokens, or even let Python know how to split up a certain sentence. Another use is to identify delimiters between columns or end of line escape characters that indicate the end of line and the beginning of another, like we saw in our SMS spam collection dataset. They can also be used to remove punctuation or numbers, clean HTML tags, or just identify some random patterns that you are interested in. A few examples of regular use cases might be confirming passwords that meet some criteria. So maybe a company requires one capital letter, one lowercase, and one special character in their passwords. You can create a regex to confirm that each new password created matches that criteria. Then the last three all kind of fall under the same broad category of searching for a certain pattern like file names. So find all the CSVs that meet this criteria or some portion of a URL. So maybe it's whatever follows .com or .org or scraping the key information from a larger document like package version numbers from a technical report. There is a lot to unpack with regular expressions. I am going to outline a few quick examples here, but there is so much that you can do with regexes in terms of searching for character patterns, character placement within a string, splitting up the strings, and so on. So, I encourage you to do some of your own exploration to learn the different patterns and the functions that can be used. You can find more details in the link here. To put this to use, the low-hanging fruit here and the primary reason that we are talking about regexes is in order to tokenize sentences or split a sentence into list of words so that Python can understand what it needs to be looking at. Right now, Python just sees a string of characters, so we need to tell it what to focus on and how to organize those characters. From our machine learning model, Python will need to split the string into what we call tokens or words so that model can learn how these tokens relate to our response variable. So in cell 1, we are going to use this RE package, which provides a lot of the functions that we will use along with regexes. So we import RE here, and then we have 3 test sentences that we are going to use to test the regular expressions. All of the tests are a sentence that just says this is a made up string to test 2 different regex methods. The first test string is pretty clean, and then the last 2 are a little bit messier, where I have inserted extra spaces and special characters. And so we are going to use these 3 test cases to thoroughly test each regex to see if it works through a range of scenarios. It's worth noting that these are sentences you could actually run onto in a job. It's not all that uncommon to have random spaces or special characters dispersed throughout your text, and you'll need to be able to deal with that. So in cell 2, the first thing that we are going to work on is using the 2 different regex methods to split a sentence into a list of words. The first approach that we'll take is using the split method from this RE package. The goal will be to identify the white space or characters separating the words and then tokenize your sentence in that way. So here's how we are going to do that. We are going to start by testing the split method on our first test string, which is the cleanest of the 3. So we'll do that by typing in re.split, open parenthesis, slash lowercase s, comma, and the name of the first test string, which is re_test. Now what this slash lowercase s tells Python to look for is a single white space to split the string. So let's run that, and on the first test string you can see that it's pretty clean, and so it's only looking for one single white space, which works pretty well on that. But let's go ahead and try this on the second test string, and so in cell 3 we'll apply re.split using \s on re_test_messy, and when you run that you can see that it's not quite as clean as the previous one. Python doesn't know what to do with the extra white spaces that are included because the regex is only looking for a single white space. So a regex this simple won't work. So in cell 4, if we copy the code in cell 3 down to the cell 4 and just add a plus sign after the s here, and that will tell Python to look for one or more white spaces. So it should be able to handle this case where we have multiple white spaces, and when we run that on the second test string again, you can see that it handles this case pretty well. The real test is going to be on the last string where it has special characters separating the words. So in cell 5, let's take the third string, which is re underscore test underscore messy1. You can see that it doesn't split it at all, and it returns the entire string all as one. When dealing with special characters as the separators between words, this simple regex can't handle that scenario. So searching for white space isn't quite robust to handle more complicated strings. So let's try a regex that's a little bit more flexible. In cell 6, we can just copy the code in cell 5, and instead of using a \s plus, we are going to change that to \W plus. Now what that regex will do is it will search for any non-word character, and it will use that to define its split. Whether it's a space, a backslash, quotes, period, anything, it doesn't care. And we are going to keep using this plus sign in here because we know that our string has more than one special characters in a row. And if we remove that plus sign here, it won't be able to handle multiple special characters in a row. So therefore we keep the plus sign. And when we run this, you can see that it works well on this most complicated version. Now I'm not going to test it, but we could backtest it against the prior two examples, and it would work really well on those ones as well. So as a recap, using the split method allows us to tokenize by finding characters that separate the words. The other option is, instead of searching for what splits the words, just search for the actual words themselves and ignore the characters that split the word. This can be done using the findAll method. The nice thing about this method is that it's the same syntax as the split. So we'll just have to change the regex that we are using. So in cell 7, we will do re.findAll /s plus re underscore test. We saw that using \lowercase s plus look for one or more white spaces. Now when we capitalize that s, it will flip it. Instead of looking for one or more white space characters, it will look for one or more non-white space characters. So we get the opposite effect. So let's start by testing this out on the most simple example. So we'll test it out on re underscore test. And you'll see that it does well on that most simple example that's just separated by single white spaces. Now in cell 8, let's copy that code down and we'll run it again on the second example, which is just adding underscore messy. So we have re underscore test underscore messy, and so this is the one that has multiple white spaces separating the words, and it still does well on this one. So let's test it on the most complicated one where we have special characters separating the words. So in cell 9, we'll just change re underscore test underscore messy to re underscore test underscore messy1, and we'll run that, and we see that it cannot handle this scenario still, because it's still looking for non-white space characters. The dashes and backslashes and periods still count as non-white space characters, so it still thinks that those are part of the word. So coming to cell 10, we need a more flexible regex. So let's copy down the code here in cell 10, and just like we did before, we are going to switch from S to W. Previously we learned that capital W plus looks for one or more non-word characters. So again, by making it lowercase instead of capital, it flips it so that it will search for one or more word characters. So basically it will search for tokens that resemble a word. So it will actually look for letters. So let's run this on the most complicated example and see if that works. It does return all the tokens that we are looking for. So again, it will search for the actual words and ignore all of the special characters, and it will properly tokenize our string and return only the words that we care about. So that's how we can use two different methods from this RE package along with several different regexes to properly tokenize message sentences. Now that we have covered some of the basic regex usage for the purpose of tokenizing, there are a few key takeaways to keep in mind. There are two methods from the RE package that can be used for tokenizing. FindAll will search for all the actual words ignoring the things that separate the words, while split will search for characters that split the words while ignoring the actual words themselves. And the regexes that are the most useful for tokenizing, keep in mind that anything using a W is based on words, while anything with an S is based on white spaces. In our daily work, it's much more common to be using the W regex because it allows the flexibility for words to be separated by spaces or special characters. But having an understanding of what the S has to offer is a nice tool to hold in your back pocket. Picking up right where we left off, understanding how regex can be used for tokenization is helpful, but let's explore another usage of regexes. So in cell 11, I've defined a sentence here, and I want to follow the Pep8 guidelines. If you are not aware, Pep8 is a style guide for Python. Now let's just say that this sentence lies in some very large document that you've put up together, and you realize that a lot of people don't know what Pep8 means. So you want to expand it to Pep8 Python style guide. However, let's assume that it's also likely that you made some spelling errors, and so instead of Pep8, maybe you had Pep7 or Pep8, which are represented by these other two test strings. So you don't feel really comfortable explicitly searching for Pep8 and then replacing that with Pep8 Python style guide, because you will miss these mistakes. So you need to come up with a pattern that will not only capture Pep8 but also your mistakes. So we want to build a process that will identify every place where Pep8 occurs plus some likely typos, and it will replace it with Pep8 Python style guide. So what we are going to do is we are going to use the findAll function that we learned previously, and we are going to test it whether it will be able to find Pep8, and then after that we find the proper regex. We can use a sub method to replace it. So we run this cell to store our test strings, and then in cell 12 we need to call the findAll function. So what's that going to do is, so that's going to be re.findAll open parenthesis, and then the regex that we are going to use is square brackets a to z, close the bracket, and then we are going to add a plus sign outside of it, and then as the second parameter we are going to pass our pep8 underscore test, which represents the first test case that we laid out above. So when we run this, it returns try to follow guidelines. So try to follow and then guidelines. So you will notice the thing that's missing in pep8 is I. So that indicates to us that the regex is case sensitive and it's only looking for lowercase a through lowercase z. So in cell 13, let's change that, and just we'll change it to capital A and capital Z. So this will again search for strings of one or more characters with capital A through capital Z. So when we run this on the first test case, pep8 underscore test, and it captures I, and it also captures pep, but it doesn't get the 8 in there. So if you recall in the earlier slide, we saw that when we added 0 to 9 within the brackets here, but what we did is actually search for letters or numbers. So it still captured the I, and it also captured any other number in the document. But for pep8, what we wanted to do is capture letters and numbers. So in cell 14, the way we can do it is by adding a bracket around A to Z and add a plus sign outside of that, and then we add a bracket around 0 to 9. So now what it will search for is strings of one or more characters with letters A to Z capitalized and numbers from 0 to 9. So when we run that, you will see that it captures pep8. Now in cell 15, lastly, let's test it on peep8 test, and it captures that. So this regex pattern is properly capturing pep8 along with two other likely misspellings. Now that we have the proper regex, the second part of this process is to replace the tokens captured by this regex with pep8 Python style guide. So in cell 16, for this we are going to use the sub function, which will search for a regex pattern, and then when it finds it, it will replace it with a given string. So the way we actually implement that is re.sub. So we'll pass in the regex that we have defined above, that is a to z plus 0 to 9 plus. And then we'll say that you find that, replace it with pep8 Python style guide, and then lastly we have to tell it what string we want to test it on. So first we'll test it on pep8 underscore test. So just as a reminder, what this should do is find pep8 or pep7 or peep8 and then replace it with pep8 Python style guide. So let's run that, and if you take a look at what pep8 test originally was, it simply just added Python style guide to the end. So in cell 7, let's test this now on pep7 underscore test and see if it still does that appropriately, and it does. So instead of pep7, it's now pep8 Python style guide. Now this regex certainly isn't perfect. You can imagine a scenario that it would miss, for instance, if there is a space between pep and 8, or if it was lowercase, it would miss both of those. So you would likely need to spend some more time refining your regex. However, the point was to illustrate how you can use regexes and give a practical example of a case that you might use it in. So now up to the point that we've explored 3 different regexes method with some practical application of how you might use it. So now up to this point we've explored 3 different regex methods with some practical application of how you might use it. But there are a lot of other regex methods within this RE package. Few are listed here. So there is search, match, full match, find iter and escape. Even more broadly, the regexes that we have explored are very simple. They can get very complex, and the best way to learn them is by defining your own string and the goal of identifying some substring. Pull up a regex cheat sheet and start exploring different patterns to try to identify that substring. Up to this point, we've learned some basics of NLP and NLTK, and we've learned how to read in messy text, and we've learned how to use regular expressions to search for and manipulate that text. Now in this section, we'll take a step back to understand how all this fits together in the broader machine learning pipeline before we dive into each step individually. Now this section is going to introduce some new topics as well, but don't worry, we'll cover each of these topics in later parts. This is just meant to provide you the proper context for how all this fits together. In a typical machine learning pipeline, you will start with some document with raw text in it, just like the SMS dataset that we are working with. It's important to note that at this stage, the computer has no idea what it's looking at. All it sees is a collection of characters. It doesn't know the word ham from the word spam. The characters mean nothing. It doesn't even know a space from a number or a letter. They are all the same. So the first thing we need to do is tokenize our text. We did this earlier in the section by splitting on white space or special characters. So you would take the sentence, example, I am learning NLP, and it would split them into a list with 4 tokens. I, and, am, and then learning. And lastly, NLP. So now, instead of just seeing one long string of characters like it was seeing before, now Python will see a list with 4 distinct tokens. So it knows what to look at. So now that we have a list of tokens, Python knows what to look at. But some of the words might be a little more important than other words. For instance, the words and, of, or appear very frequently, and they don't really offer much information about the sentence itself. These are what are called stop words. We took a quick look at these in the earlier section. Typically, you will remove these words to allow Python to really focus on the most pivotal words in our sentence. So, in the example that I used previously, instead of a list with I am learning NLP, once you remove these stop words, now you are just left with learning and NLP. This still gets across the most important point of the sentence, but now you are only looking at half of the amount of tokens. Also, the process of stemming helps Python realize that words like learn, learned, and learning all have basically the same semantic meaning. You may not think that this is a big deal, and in a small sample, it's really not. But when you suddenly have a million of text messages and a corpus of 150,000 words, any words that you can remove to allow Python to focus on the most pivotal words can really make a big difference. Okay, so now Python sees a list of tokens that you care about and the keywords that we think are useful for building some kind of machine learning model. Even though Python now knows what you care about, it still only sees characters. It doesn't know what learning or NLP even means. So now that we have to convert it to a format that a machine learning algorithm can actually ingest and use to build a model, this is a process called vectorizing. We'll talk about this more in detail in the next section, but it's basically converting the text to a numeric representation of the text, where you are essentially counting the occurrences of each word in text message using a matrix with one row per text message and one column per word. Again, don't worry about understanding this fully right now. We'll cover this in much more detail in the vectorization section. So now that we have this numeric matrix, you can now fit your actual machine learning model by feeding in your vectorized data along with your spam or ham labels. This model will then learn the relationships between the words and the labels in order to train a model to make predictions on text messages that it has never seen before and determine whether they are spam or not spam. There are various types of machine learning models. It will be up to you to select a few of them to try out. You will tailor your choices based on the type of input data that you are giving it, what you are trying to predict, and how much compute power you have, things like that. You will typically test out a number of what's called candidate models before selecting the model that performs best. Once you select the best model, you will evaluate that on a holdout test set, and this typically is a set of data that you will set aside in the very beginning for the purpose of testing your final model to see how your model will perform on data that it has never seen or touched before. If it passes this final test, then you will prepare to implement it within your framework that you are working with. In this example, it's an illustration of a spam filter trying to filter out whether an incoming email is spam or not spam. If you are not familiar with a typical machine learning pipeline, this can be a little bit confusing. But don't worry, it will make more sense as we dive down deep into each topic within the next few minutes. So let's jump into actually implementing steps 2 and 3 of this pipeline. So we've talked about a few different concepts throughout this lecture. In the previous slide, we put those together at a conceptual level, laying out what the full machine learning pipeline looks like. In this notebook, we are actually going to write the code to handle the cleaning portion or the pre-processing as it's typically referred to of the machine learning program. There are 4 steps that you will see in a lot of text cleaning pipelines: removing the punctuation, tokenization, removing stop words, and lemmatizing or stemming. We are going to focus on the first 3 steps in this notebook, and then we'll cover lemmatizing and stemming in the next notebook, as those are a little bit more advanced topics and not implemented in every pipeline. So, in cell 1, in the beginning of this script, we'll ingest some raw text, and by the end, we'll have that text all cleaned up and prepared for vectorization step laid out in the last section. It's worth noting here that there are custom packages that do most of this for you, like the tokenize function that we saw from NLTK earlier. But I want to walk through this step in detail to illustrate how the system works under the hood. So first, we'll read in our data and we'll use the same SMS spam collection dataset that we've been working with. We'll need pandas to read in this data, so we'll go ahead and import it here. And then we are going to do something new by setting a custom value for how many characters we can see in a pandas data frame when we print it out. So we do this by simply calling pd, which refers to pandas, dot set option, and then the option that we are passing in is display.max column width. and then we pass in 100. Again, the default here is 50. We are just changing it to 100. So now we are going to read in the data using the pandas read CSV function that we have seen before, indicating that it's a tab separated file and that there is no header. So we'll define the column names and then we can go ahead and run that cell. So you will even notice here that this is printing out much more of the actual text message than we saw previously because we widened the column. In cell 2, before we dive down into cleaning up this dataset, I want to quickly show you where we are trying to go with this. So I went ahead and cleaned up this data ahead of time, and I'll read that in just to give you some direction and understanding of what we are working towards. So when you run this cell, now you will notice that the body underscore text column is the raw text that we saw above, and then body underscore text underscore no stop column is the cleaned up version. So there is no punctuation within the words, they are all split into tokens, and you will see that all the stop words are removed. For instance, just looking at the first row, you will notice that been is gone. You will notice that for and the are gone. They are not present in this list over here. So this is where we want to get to, and over the next few minutes we'll piece together the tools that we need to get this cleaned version. So now we have a decent idea of where we want to go with this dataset. The first step that we are going to take is to remove punctuation. Now in cell 3, in order to remove punctuation, we actually have to show Python what even a punctuation looks like. Luckily, the string package has a list of punctuation in it. So I'll go ahead and import string, and then all we need to do is just call string.punctuation, and we can run that, and that will just print out a list of different punctuation. So this is really helpful to allow Python to identify what we are looking for here. The reason that we care about this is that periods, parentheses and other punctuation look like just another character to Python, but realistically the period doesn't really help pull the meaning out of a sentence. So in cell 4, for instance, for us, I like NLP with a period is exactly the same as I like NLP. They mean the same thing to us, but when you give that to Python, Python says that those are not equivalent things, and Python isn't saying I like NLP without a period is different than I like NLP with a period, in that they are really close, but one has a period and one doesn't. To Python, these might be well as I like NLP versus I hate NLP. It knows that they are different without any ability to understand how different they are. In order to clean this up, we would want to take a list of punctuation and tell Python basically whenever you see anything like this, you want to remove it. So in cell 5, we are going to build our own function to remove this punctuation. And conceptually, what we want Python to do is cycle through each character and check if it's some kind of punctuation. If it is a punctuation, discard it. And if it's not, then keep it. So we are going to use a list comprehension to develop that functionality. List comprehension makes it easy to cycle through elements, check if they meet some condition, and then just return if they do meet that condition. So let's go ahead and build this function. So we are going to call it remove underscore punctuation, and we open and close parentheses, and within that we are going to pass in some text. So that's what it expects, and now we build on our list comprehension. So I'm going to walk you through the actual of what we are going to type here, and then I'll revisit it and explain the syntax. So what we are going to type in is character for character in text, if character not in string.punctuation, and then we'll just assign this to text underscore no punctuation. In terms of the syntax of list comprehension, let's focus just on the part that I have highlighted so far. So we are saying character for character in text. So what this is saying is that for the text that we passed in, return each character for each character in the text that's being passed in. So what this will do is it will create a list and it will just store a character in each element of that list. Now, the condition that we are really concerned about here is that we want to make sure that each character is not a punctuation. So now this entire thing is saying return the character for each character in text as long as that character is not in the string of punctuation. So this text underscore no punctuation will be a list of characters that are not punctuation. Then we are going to wrap this in a join function. It will take this list that this list comprehension is generating and it will join each individual element to one another. And the only catch is that join function needs to know how to join these things together. So if I indicated a space there and hit dot join, what that would do is it would create space between characters of the sentence. So we want to tell it that it is joining on nothing. So we don't give a space between them. So at last we need to return text underscore no punctuation. And then in order to apply this to our dataset, we are going to use what's called the lambda function. So first we are going to define the name of the column that we want this clean data to be passed into. So we'll call it body underscore text underscore clean, and then we'll set that equal to the column that we want to call this function on. So we want to call this remove underscore punctuation function on data body text, and then in order to apply the lambda function, what we do is we type dot apply lambda x colon remove punctuation x. And so what this will do is it will apply the function that we just wrote to each element or each row of body text, and so that will remove all the punctuation and then return a column called body underscore text underscore clean. So let's just print out the first 5 rows and run it. This will recreate our sentence. So if we go ahead and run that, now you can see that it's joined right back all together as a sentence. So that's how you remove a punctuation from a string. Next, we learn how to split this string into a list of tokens. Now that we've removed punctuation in cell 6, we can move on to tokenizing our text. We discussed previously tokenizing is splitting some string or sentence into a list of words. And we learned that you have to account for cases in your strings, like if they are separated by special characters or multiple spaces. So we'll just use that what we've learned in our previous section about regexes and combine that with our approach that we learned in the previous section where we removed punctuation by writing our own function and then applying it to the dataset using a lambda function in order to tokenize our text. So you'll use the same RE package that we used last time, and then we are going to go ahead and define our own function and we call it tokenize, and it will accept some text. So the first thing that we are going to do again is call this re.split function, pass in the regex that we want to use, which is going to be this capital W plus, and then as the second parameter into the split function, we'll just pass in text, which is what's being passed in, and then we need to assign that to something, and we'll just assign it to tokens, and then we will want our function to return that list of tokens. So just as a reminder, this slash w plus regex indicates that it will split whenever it sees one or more non-word characters. So that will split on white spaces, special characters, and anything like that. To apply this to our dataset, we now need to make use of the lambda function just like we did earlier. So in this cell, we are going to use body underscore text underscore clean column that we had created in our previous cell. And just like we did previously, we'll use dot apply lambda x colon tokenize x dot lower, and I'll return to the dot lower in just a second. So this will take the tokenize function and apply it to each element or each row of body underscore text underscore clean. Now we need to assign it to a new column, and we'll call it body underscore text underscore tokenized. So let's print out the first 5 rows, and then when we run that, you see that it's taking this sentence and it's properly split each word into its own entry in the list, and they are all in lowercase. Now just to circle back to this lower method, this isn't necessary for this function in particular, but it will be necessary moving forward. So in cell 7, you see that Python is case sensitive. So if you give it capital NLP and ask it if it's the same as lowercase NLP, we know that that's basically the same thing. But if you run that for Python, Python says that those two things are different. So when we get to further steps, now Python is seeing capital NLP something totally different from lowercase NLP, and it has to learn all those things that are closely related. But we don't want it to consume its resources by learning things that are related. So we want to explicitly tell it that those are the same things. So that's why we apply the .lower method. So now we have a nice clean list of words without any punctuation. So now Python knows the tokens or components that it's supposed to be looking at. The next step will be to remove some of the irrelevant words in these lists. So we are almost through the basic cleaning steps now, and thus far we've removed punctuation and tokenized to create a list of words out of a sentence. The last step in cleaning up this data is to remove stop words. Now we've discussed stop words previously, and they are commonly used words like the, but, if that don't contribute much to the meaning of a sentence. So if we want to remove them to limit the number of tokens Python actually has to look for when building our model, for instance, take the sentence I'm learning NLP. After tokenizing it, we would have 4 tokens: I, am, learning, and NLP. Then after removing stop words, instead of a list with 4 tokens, now you are just left with learning and NLP. So it gets across the same message, and now your machine learning model has to look at half the number of tokens. So coming to cell 8, I'll use this NLTK package that I introduced earlier, and this has a nice built-in set of stop words. So we'll call that using nltk.corpus.stopwords.words, and we have to tell it that we want English stop words. So we can run that, and now for removing these words, this isn't going to be anything new. So in cell 9, we are going to define our own function, and we use the same type of list comprehension that we used to remove punctuation above. Now we are just going to use stop words as our exclude list instead of punctuation, and then we'll use the lambda function to apply it to our dataset. So the name of our function is going to be remove underscore stop words, and it will accept a tokenized list. So that's important that what we'll be passing in it is a list of tokens, not a full sentence. So now for our list comprehension, it will follow the same syntax as before, and we are going to change the variable names. So now we are going to say I want to return word for word in tokenized underscore list if that word is not in stop word, and then we can assign this to text. So once again, this will just cycle through our list of tokens that we had generated in the last cell and check if each one is a stop word. If it is, then it will toss it, and if it's not, it will keep it and return it to the text in the form of a list. Now we want to tell this function to return text, and we want to apply this to our dataset. So we are just going to use a lambda function like we have used before, and we'll store it in body underscore text underscore no stop, and we'll set that equal to body underscore text underscore tokenized, and then we'll apply our lambda function and call remove underscore stop words on that x. So again, this will apply our function to each row in our dataset on this column, and it will store in the body underscore text underscore no stop. And so let's go ahead and print out the first 5 rows of that. So you'll notice that the first row, the words been and for and the are now gone in our new list. And for instance, in the second one, you'll notice that in and a are gone. So now we have a cleaned column that has been tokenized. We've removed all the punctuations and we've removed the stop words. So this is a very abbreviated look at what a pre-processing pipeline looks like when you're preparing your raw text into a format that a machine learning model can actually use. Next, we'll explore some extra and slightly more advanced cleaning techniques and concepts that we can apply to our text to further help a machine learning model focus on things that are really important. So till now, we've learned the basics of preparing our text to build the model. We learned how to remove punctuation, tokenize and remove stop words to provide a clean list of words to Python. Now, in this part, we are going to learn how to take our cleaning one step further and to provide the model with better information for classifying the text. We'll introduce the concepts of stemming and lemmatizing. Let's start with stemming. So, what is stemming? The formal definition of stemming is the process of reducing inflected or derived words to their word stem or root. More simply put, the process of stemming means often crudely chopping off the end of a word to leave only the base. So this means taking words with various suffixes and condensing them under the same root word. Recall, when we removed stop words, it was to reduce the number of words Python has to look at or consider. Stemming is shooting for the same goal by reducing variations of the same root word. If that doesn't make sense, let's jump into examples to see what it means in practice. So here we have a collection of sets of 2 or 3 words. The words in each set have similar meaning. So stemming and stemmed are two distinctly different words and Python will not inherently know that these are even related. What a stemmer will do is, it will reduce stemming and stemmed down to their base word of stem. So now, if stemming and stemmed are both represented by stem, we retain the semantic meaning of both words, and now Python views them as the same. Similarly, for electricity and electrical, they are pared down to electric. Berries and berry is interesting because it's more than just cutting off the end of it, like we've seen previously. The stemmer will chop these down both to berry with an I. Lastly, connection, connected and connective will all be chopped down to connect. So this seems pretty useful, but stemming also uses very crude rules, so it isn't perfect. For instance, look at meaning and meanness. These words aren't really all that closely related, but they'll both be stripped down to a base of mean, and thus Python will think that meanness and meaning are the exact same thing. So stemmers are correct in most cases, but the trade-off with these simple rules is that it won't always be right. So all this seems to be pretty interesting, but why do we really care about this? Why does this actually help us for model building? Well, if Python sees grew, grow and growing as 3 separate things, this means that it has to keep those 3 separate words in memory. Imagine every variation of every root word. Maybe we have 1,000 root words, but in our corpus we have 2,000 total words with every suffix added to the root words. The alternative in this grew, grow and growing example is applying the stemmer, and now it only has to know what grow means, as each variation of grow is simply replaced by grow. So Python has to look at a lot more tokens without a stemmer, and it doesn't know that these separate tokens are even related. So the benefits of a stemmer is it reduces the corpus of words the model is exposed to. So it's just grow instead of grew, grow and growing, and it explicitly correlates words with similar meaning. So Python could learn through the training process that we'll discuss later that grow, grew and growing are similar in meaning, but it also may not. It depends on a lot of different factors. In this case, we are not leaving it up to Python. We are being explicit by replacing similar words with just one common root word. There are a number of different types of stemmers that use various algorithms and methods to generate the stemmed version of words. A few that are included in NLTK package are the Porter stemmer, the Snowball stemmer, the Lancaster stemmer, and a regex-based stemmer. We'll be focusing on the most popular stemmer in the list, that is the Porter stemmer. So next, we'll learn how to use the Porter stemmer. Now that we've learned what stemming means, we are going to put it to use. And we'll do this in two stages. First, we'll test out our stemmer on specific words to understand how it works. Then, we'll apply the stemmer on the SMS spam collection dataset to further clean up our data. So, first in cell 1, we'll import the NLTK package, and then from that NLTK package, we'll call the proto stemmer and store that as PS so that we can call it later. Then in cell 2, let's use the dir function to see what attributes and methods are contained within this proto stemmer. So we see that there are a lot of different attributes and methods that you should explore, but this stem method is really the one that's used most commonly, and it's the one that we'll be focusing on here. So now let's look at how the stemmer will handle a couple of examples. In cell 3, let's try out this grows, growing and grow example that we've been looking at. So we'll start with ps.stem, and then we just have to pass in the word that we wanted to stem. So we start with grows, and then we'll add growing for the second one, and then for the last one we'll leave that as just grow. Now because we have three function calls in the same cell, Jupyter will print out the result of the last one, but we want to print out all of them. So we have to explicitly tell it to print out all of these three. So therefore we add a print call for each of the three. And then when we run it, we see that it reduces them all to the proper root word of grow. So now these three words can be treated as the same word, and rather than Python seeing them as three distinctly different words. So now in cell 4, let's look at one more example. So we showed that in slides how the stemmer isn't perfect, where it stemmed both meaning and meanness down to mean, even though they don't represent the same thing. However, if you look at a different example that could be a little difficult, we'll do run, running and runner. You could see that how all of these three might be reduced down to just run, even though the first two are actions and the last one describes the person. So let's run it. And we see that the stemmer can actually tell that the first two are different than the last one in some way. So stemmers aren't perfect, but they still do a pretty good job of identifying what words have the same meaning. Alright, so now that we've learned a little bit about how the stemmer works on toy examples, let's apply it to the dataset that we've been using, that is the SMS spam collection dataset. So coming to cell 5, let's just start by importing the packages we need to read in the text and clean up our data. So we'll be importing pandas, the RE package and then the string. Then we'll also call the same option that we used in previous notebooks to display more of the text message. And then we'll store our stop words as stop words for use when we clean up the data. And then we'll read in the data and assign column names in the same way that we did previously. Now let's just print out the first 5 rows. And you will see just as expected, and again remember this is the raw text, this isn't the cleaned version. So coming to cell 6, now for cleaning of the text, this function is exactly what we put together previously, but I just collapsed the three functions down into one. So we still have the same components. So we remove the punctuation in the exact same way. We tokenize it and then we remove stop words, and then we use the lambda function to apply it to the dataset. So let's just call the first 5 rows and run that to make sure that it prints out what we expect. So this is your tokenized list without any punctuation or stop words, and it just looks like how we ended the pipeline. Now in cell 7, let's get into some new stuff. So we saw that ps.stem method is what stems each word. So the column that we'll be operating on from this data frame is this tokenized list. So we'll want to iterate through the list and stem each word and then return the stemmed version back to the list. So this should be starting to sound familiar at this point. We'll again write our own function using ps.stem within our list comprehension in order to stem each word. So let's call our function stemming, and then it will accept a tokenized list of text. Now if we recall with list comprehension, the way that we'll define it is word for word in tokenized text, and we'll assign that to text. So this will just return each word for each word in tokenized text. In other words, it will take each word in this list and just output each word. So all we need to do to stem it is just say, instead of returning the original word that was in the list, apply the stemmer to that and return the stemmed word. So then that will store all the stemmed words in a list called text, and it will just return that text. And lastly, like we did before, we are going to use a lambda function to apply to our data. And then let's store it in a column called body text stemmed. And then we are going to run our lambda function on body text no stop. And then we want to apply the stemming function using this lambda. So we'll do lambda x stemming x. So again, this will apply the stemming function to each row in our data frame. So we are going to run that and print out the first 5 rows. Now it's worth noting that the stemmer won't do a great job with slang or abbreviations. So it's probably not a great fit for a text message dataset. I'll call your attention to a couple of things. First, entry is changed to ENTRI. That's entry with an I. So it could also accommodate plural entries. Same thing with WKLI. Another one is on the second line. Lives is reduced down to live. So now you've learned that what stemming represents and how to actually apply it. Stemming helps us reduce the corpus of words that the model are exposed to, and it explicitly correlates words with similar meaning. So in the next section, you'll learn about lemmatizing, which is a different way to accomplish the same goal. Now we'll be learning about a related but slightly different tool called lemmatizing. So what is lemmatizing? The formal definition is that the process of grouping together the inflected forms of word so that they can be analyzed by a single term identified by the words lemma. The lemma is the canonical form of a set of words. For instance, type, typed, and typing would all be the forms of the same lemma. More simply put, lemmatizing is using vocabulary analysis of words to remove inflectional endings and return to the dictionary form of a word. So again, type, typed, and typing would all be simplified down to type because that's the root of the word. Each variation carries the same meaning, just with slightly different tense. So you might be thinking, this sounds an awful lot like stemming, and you won't be wrong. They are trying to accomplish the same thing, but they are just doing it in slightly different ways. And in practical terms, there's an accuracy and speed trade-off that you're making when you opt for one over the other. The goal of both is to condense derived words down into their base forms, to reduce the corpus of words that the model is exposed to, and to explicitly correlate words with similar meaning. The difference is that stemming takes a more crude approach by just chopping off the ending of a word using heuristics without any understanding of the context in which a word is used. Because of that, stemming may not actually return an actual word in the dictionary. And it's usually less accurate, but the benefit of that is it's faster because the rules are quite simple. Now, lemmatizing leverages more informed analysis to create group of words with similar meaning based on the context around the word, part of speech, and other factors. Lemmatizers will always return a dictionary word, and because of the additional context it's considered, this is typically more accurate, but the downside is that it may be more computationally expensive. So this is a very brief introduction into lemmatizing. Instead of offering examples of how a lemmatizer works, I am going to save that for the coding notebook, as I want to illustrate some of the differences between how a stemmer handles certain words and how a lemmatizer will handle those same words. Now that we've learned about what lemmatizing means, we are going to put it to use. So we'll do this in 2 steps. First, we are going to test out the lemmatizer on specific words to understand how it works, and then we'll apply it on the SMS spam collection dataset to further clean it up. So the same process that we saw on the stemming notebook, we are going to apply with lemmatization. Just like we saw with the stemmers, there are few different lemmatizers as well that handle words in slightly different ways. So we are going to use the WordNet lemmatizer. This is probably the most popular lemmatizer. WordNet is a collection of nouns, verbs, adjectives, and adverbs that are grouped together in sets of synonyms, each expressing a distinct concept. The lemmatizer runs off of this corpus of synonyms. So, given a word, it will track that word to its synonyms and then the distinct concept that the group of word represents. You can read more about this at the WordNet website right here. In cell 1, we are going to import the NLTK package and then we'll call the WordNet lemmatizer from that package and store it as WN to be used later. We are also going to call the Porter stemmer again and store that as PS. This is so that we can test out how these two methods handle the same words differently. Now in cell 2, we'll call the dir function with the WordNet lemmatizer to see what attributes and methods are contained in there. The one that I am going to call out is the lemmatize function. This is the one that we'll be using in this notebook and it's the most commonly used function from this tool. So when we looked at stemming, we mentioned in the slide that meanness and meaning were both condensed down to mean. So Python would now assume that meaning and meanness were exactly the same, which is inaccurate. In cell 3, let's confirm that by printing out the stem from the Porter stemmer. So ps.stem for meanness and meaning will return mean for both of them. Now coming to cell 4, let's explore how the lemmatizer might handle these differently. We'll have to do print again and this time call the WordNet lemmatizer .lemmatize meanness for the first one and then with meaning and then we run that. Also note that this takes a little bit longer than the stemmer. Again, because it's not just using a simple set of rules to chop off the suffixes. It's actually tracking it against the synonyms to find what group these fit into. You will notice that both of these were untouched. This brings us to an important point, and I'd like to highlight two things. First, stemming uses the algorithmic approach and so it's only concerned with the string that it's given and it will essentially chop off the suffix. Lemmatizing is a bit more complex in that it searches the corpus to find related words and condense it down to the core concept. The problem is that if the word isn't in the corpus, then it will just return the original word. So that's what's happening here. With that said, not condensing in this case is still probably better than incorrectly stemming it using the Porter stemmer. So that's one example. In cell 5, let's look at one more example. Let's do stemming on goose versus geese. These are clearly related. One is just the plural of the other. Let's just run the stemmer on that and you will see that the stemmer doesn't know quite what to do with goose and geese. So it returns two different root words. So again, Python will still view goose and geese as two different things even if you use the stemmer. Now in cell 6, let's try to use lemmatizer on goose and geese and see if the lemmatizer is any better at handling these differences. You will see that the lemmatizer correctly maps both of these back to goose. Python will be able to now realize that these two are the same words. So a lemmatizer can be quite powerful in some relatively complex situations. Now that we've learned a bit about how lemmatizer works in cell 7, we are going to do the same thing that we did with the stemming notebook, where we are going to read in our SMS collection spam dataset and clean it up by tokenizing, removing punctuation stop words, and then we'll apply the WordNet lemmatizer at the end. Now reading in our SMS spam collection dataset in the same way that we have in the past few notebooks and assigning the column names, let's just print out the first 5 rows to make sure it's reading in as we expected it. And then in cell 8, just as we saw with the stemming notebook, we are defining our clean text function where we have separate lines for the punctuation, the tokenizing, and the removal of stop words. And then we apply it to our dataset using a lambda function again. And we'll just print out the first 5 rows to make sure it's doing what we expected and it's removing our tokenized list without stop words or punctuation. Now in cell 9, let's jump into the limitizing portion of this. We saw before that wn.limitize is what applies the limitizer for each word. The field that we'll be working with is the list of words in the body underscore text underscore no stop. And so we are going to do exactly what we did in the stemming notebook by using list comprehension to iterate through the list of tokens and then return the limitized version. Let's define a function that we'll call limitizing, and it will expect to be passed in a tokenized list of text. And then we'll define our list comprehension in the same way that we have done in the last few notebooks. So word for word in tokenized underscore text, and again we'll assign this to text like we did in the stemming exercise. We'll just apply our limitizer here so that it returns the limitized version of the word instead of the original word, and then we'll tell this function to return that text. And lastly, we'll apply the lambda function to clean our dataset. We'll tell it that we want to store the cleaned version in body underscore text underscore limitized, and then we want to apply this on body underscore text underscore no stop. And then we'll apply the lambda function, that is lambda x colon limitizing x, and then we'll go ahead and print out the first 10 rows. We have this new cleaned up column, and I'll call your attention to a couple of things. Just like the stemmer, the limitizer won't do particularly well with slangs or abbreviations, so it's not ideal for this kind of dataset. It might be more effective if it was used on a collection of book reports or journal articles. I will call your attention to a couple of things that the limitizer was able to impact. It transitioned this lives down to life, and it also transitioned mobiles into mobile. And so you'll notice that these aren't super interesting examples necessarily. But as you saw before, the limitizer can do some relatively sophisticated things, at least more sophisticated than the stemmer. Now you've learned about what limitizing is and how to actually apply it. So both stemming and limitizing help us reduce the corpus of words that the model is exposed to, and it explicitly correlates words with the similar meaning. The limitizer is typically more accurate than the stemmer, but the trade-off is that it takes a little bit longer to run. Based on your machine learning pipeline, if the limitizer is going to be a bottleneck, then you may opt for the more simple stemmer. These demonstrations were very much geared towards just introducing you to the tools and learning the extreme basics to apply it. I encourage you to dig in further to learn more about these tools.